Good day, ladies and gentlemen. This is the 14th B presentation related to the introduction to the RM software for filter design. We will be talking within this presentation about the parallel active switched capacitor circuit synthesis. Here is the content of the presentation. First, we will be talking about introduction into the subject and rationale of the technology. Then we will speak about the decomposition of the transfer function into a form of sum of partial fractions, which is necessary for parallel realization. Then we will say several words about prewarping of the original or prototype function, which was subject of discussion in the previous presentation. Also, then we will continue with the implementation of bilinear transform, which is again a continuation of the previous lecture. And then we will proceed with parallel synthesis and description of the cells. A short discussion of the SC parallel program as part of the RM software will be given, and finally an example of realization. The analogy between a resistor and a switched capacitor is bringing a specific opportunity for creation resistorless circuits, are very convenient for integration and implementation at audio frequencies. Namely, at audio frequencies, the values of the circuit elements, resistors and capacitors, become large. And since the resistor additionally has parasitic elements and it is noisy, one would be very happy to substitute them with something else which occupies less area and preserve accuracy, which is also a problem with large resistances. Here is the basic of the switched capacitor theory. If the switch above on the left is commutated by two sequences of non-overlapping pulses as shown on the left, the above analogy will be valid if the frequency of commutation is properly larger than the signal frequency, at least twice. The value of the equivalent resistor is shown here as a reciprocal of the product of the sampling frequency and the capacitor used. To perform parallel realization, one needs first to decompose the transfer function into a partial fractions, a sum of fractions. Here is the expression of the conversion. Of the left-hand side, we have the transfer function, which is represented as a ratio of two polynomials expressed as products. On the right-hand side, we have the same transfer function expressed as a sum of a ratio of a constant, which is called a residue, and a difference between the frequency and the value of the pole. This form, in fact, since it is summation, allows for parallel realization. Of course, since the poles are complex numbers, which are have conjugate partners, counterparts, so by putting together the conjugate pairs, we transform the transfer function into one containing two type of summands. One is second order and the other is first order. Note the second order, no matter where the pole is always has always a numerator, which is of first order, and so it is a low pass since its value at infinity is 0, and the slope at infinity is minus 6 decibels per octave. Now, as already mentioned earlier, we start with the analog or S-domain transfer function, but to get the Z-domain transfer function, we implement bilinear transform, and of course, before that, we are performing prewarping in order to compensate for the nonlinear distortions which are introduced by the bilinear transform. So new functions in the S-domain are obtained in this way. And now the S-domain transfer function is prepared, and the bilinear transform may be implemented. After implementation, the second order cell becomes like this shown here. Below are formulas which are explaining the calculation of the coefficients if the biquad in the Z domain. This is the same story, but for the first order cell. Here, the overall structure of the switched capacitor filter seen as a system is described. As we can see on the left-hand side, it is driven by an analog source. Here it is a voltage source. And the signal is taken into a sample and hold circuit, which produces at node 1 a discretized input voltage. This discretized voltage is driving all cells and each one of them is producing an output according to its transfer function. All the results are taken to the summing amplifier, which produces a discretized output voltage. To get the analog voltage, to get the analog signal, one needs to implement anti-aliasing filter, which in this case, in the case of the SC parallel program of the RM software, consists of cascade of two second-order low-pass cells realized as active RC circuits. In that way, a rather good selectivity is obtained of 24 decibels per octave as asymptotic attenuation, so eliminating all higher frequencies related to the switching and sampling. Now, let's go to the cells. First, we see here the second order high quality factor biquad switched capacitor cell, which is used in the RM software and more specifically in the SC parallel program. Here is its low quality factor counterpart, and this one is the first order cells, which makes a complete set of 3 cells necessary for parallel synthesis of active SC filters. To complete the part of the system which contains switches or the commutating part, one is the summing amplifier, and here is the summing amplifier used within the RM software. What is characteristic here that the sign of the summation or the weighting sign of the summand may be controlled by simply exchanging the controlling signals of the switches. Instead of phi 1, put phi 2 and vice versa. That simplifies the summing as compared with the case of RC filters where separate inverters are needed. And that would be all about the structure. Here is a story of the program as such, which performs synthesis. It produces a textual report containing all the data necessary to follow the synthesis process and the results. Then there is a report in a form of an HTML file which depicts the schematic tool in addition to all information. Then a CSV file is produced which allows for graphical presentation of the transfer function results, not simulation, but transfer function after bilinear transform, and in the frequency domain. And finally, there is a SPICE file, which is supposed to be used for time domain simulation of the obtained system or circuit. This SPICE file contains all sample and hold, parallel connected cells, summing, and anti-aliasing. Here is an example related to the sixth order all-pass Bessel filter. The cutoff frequency here is chosen as shown. When I'm saying the cutoff frequency, that it was used for the synthesis of the low-pass prototype, which was used to create the all-pass filter by adding the transmission zeros, which are mirrored against the omega axis. So here are the zeros and the poles of the filter, of the all-pass filter. 3 cells, Biquat cells of this type were used. Here are the capacitance values of the cells. Here are capacitance values for the summing. Here is 1 out of 2 schematic of the anti-aliasing filter. 2 such cells are connected in cascade. And this is the sample and hold. In fact, the simplest of all, which is implemented in the SPICE description of the filter synthesized by the SC parallel program. Now the time domain simulation is here shown. When you look to the FSIM above, we see the star 0.5, which means this is half of the cutoff frequency of the filter. That is the frequency of the signals shown below. Now we see 2 signals. V1 is the input signal, and V all means after both anti-aliasing cells is in the red line. As we can see, these values are not equal. The reason for that is the added gain of the filter at 0th frequency, which is so they are different by a constant. This constant is of course preserved even if the frequency is risen 10 times. It is an all-pass circuit, and the response should be constant amplitude-wise, which confirms the success of the synthesis process performed by the SC parallel program. Before conclude, we will mention some issues related to the switched capacitor result reported here. Namely, to do the simulation in the frequency domain, it is possible to make transformation of the final circuit and simulate it to get the frequency response. In real life, however, we are building circuits of switches and operational amplifiers and capacitors, and that is why we are here keeping the time domain as a reference 1. That, of course, brings several problems related to the very run of the simulation and of the quality of the results, or better to say, the information obtained from the simulation. First, since switches are used and switches are defined with thresholds and on and off resistances, in complex circuits and fast switching, have in mind that the pulse trains used to control the switches have edges which may be short or long depending on the designer. So all these may prevent success in simulation. Not only it may influence the simulation results. Due to the algorithms implemented to control the switches, it may happen even that the simulation is stalled. And in that case, one needs to accommodate the model of the switch, which is out of the scope of this program. In addition, the SC parallel, as do all the programs within the RM software, uses an ideal controlled voltage source with very high value of the gain as a model of the operational amplifier. In the case of switched capacitor circuits, since they are low-pass circuits, there are no problems related to the frequency response of the operational amplifier. But since there is switching, it may be a problem when implementing real operational amplifiers with finite slew rate, and to obtain that may bring results which are not ideally equal to the ones reported here, which are also out of the scope of the synthesis program, since we never know in advance what will be the operational amplifier used by the filter designer. So that would be all about the synthesis of active SC filters as a parallel. Thank you very much for your attention.